Javier Redondo. We talk about weakly interacting slim particles.
Okay, please tell me if you cannot hear me from behind. So my task was to give a review on the bounds and constraints that we have for regarding the existence of weakly interacting slim particles, the particles we've been hearing in this last hour, which is something that cannot be done in 30 minutes, unfortunately. So instead of doing that, I decided to elaborate a little bit more on the hints from astrophysics and cosmology that Mark was speaking about, because they are telling us indeed something about the bounds, and because they are more optimistic and they are more interesting probably for you to really find out possible hints from your high energy theories. So my outline, well, and as Mark was saying, my talk is much more pictory, so my outline is in pictures. So I will just provide with a very naive theoretical appetizer for you all, and then I will jump up to discuss the effects of wisps in cosmology, especially the role as dark matter and dark radiation. Discuss a little bit the anomalies of astrophysics that might point the existence of these wisps, and then, if in time, I will elaborate a little bit on the most important laboratory searches. So here's my theoretical appetizer. So from an experimentalist point of view, one would say that the standard model is a fantastic theory that makes us all very happy. However, for this audience, I think one has to underline the fact that it actually feels certainly extremely incomplete, that it does not provide any kind of physical picture of what is nature telling us. So also for this audience, what we are expecting is that when we probe physics at the smaller and smaller scales at high energies, what happens to be the standard model is just only a small piece of a much more beautiful and symmetric theory, which inevitably will contain a lot more of, well, I don't know, inevitably for this audience, stringy oriented, will contain a lot more of structure, a lot more of fields, and will be, however, much more symmetric and beautiful. The point is that when in building these theories, we sometimes happen to find that there's low energy physics implying in our models. So that even if building this high energy theory with all these wonderful muscles around, the consistency of the theory points us to the existence of a low energy degrees of freedom. So this is what we can picture as weakly interacting slim particles. So they must be the existence of these low mass particles can be related to the high degree of symmetry in our high energy theory, or simply to the complexity and the plethora of possibilities. And the fact that these particles that arise here in a hidden sector are weakly interacting might be related with the fact that they connect with the standard model only via the high energy theory. And for me, and this ends the first part of the appetizer, the paradigmatic example of that is the strong CP problem and the axion, which I don't know if I have to review or not. So you all know, perhaps you don't, I don't know, let's do it. So the strong CP problem is a problem that has the standard model as a whole, because we have a fantastic theory for to describe the strong interactions, which is QCD. But unfortunately, QCD is not a theory, it's an infinitely many, so there are infinitely many theories of QCD, each one being different by the existence of this topological term with a different coupling constant, with a different so-called theta angle. And this term generically, so QCD-like theories generically violate parity and time reversal, which would lead to CP violating, or parity and time reversal violating observables like the Newton electric dipole moment. Okay, at a level which is, so the Newton EDM would appear at a level which is of course proportional to the amount of parity and time reversal violation, and which is nearly maximal. Okay, essentially the size of a neutron multiplied by the electric charge and the theta angle. And but the strong CP problem is also a problem of not only of the QCD not only of our theory describing the strong interactions, but also of the matching between QCD and the rest of the standard model of the electroweak sector, because there's also CP violation in the electroweak sector, and we plug them in. It turns out that some part of the CP violation that we think that there should be in the electroweak sector jumps and contributes to this term here because of the anomaly. So actually, this theta term is the contribution has two contributions, one from QCD and the other from the standard model. And when one goes to an experiment and tries to measure for instance, the neutron EDM, one finds that actually is there is not there, and one can put a constraint on the theta, which is amazingly small. This would make the theta the parameter of the standard model, which is smaller, I think, the dimensionless parameter of the standard model, which is smaller. So then the strong CP problem is why this parameter is so unnaturally small. So, and one solution that was proposed in the late 70s was precisely following the scheme that I was giving you before, that there's a symmetry in the high energy part of the theory, in the high energy completion of the theory, which is axial, which is global, and it's only broken by a color anomaly, and it has to be necessarily spontaneously broken, and also at the high energy scale. And if one puts all these things, one gets a fantastic new particle, so belonging to the right leg, which is the axion. And the axion, because of it's a Goldstone boson, and because of being being related to a color anomaly, anomalous symmetry, it appears adding up to the theta term in QCD, and just because of normalization reasons, and the axion always appears divided by the so-called axion decay constant, which is a free parameter in principle, and is related with the scale at which the symmetry is spontaneously broken. So it turns out that actually QCD builds a potential, sort of, has to necessarily build a potential for this field, and actually turns out that the minimum of this potential is at the effective theta equals 0, which solves the strong CP problem very nicely. So the axion field adjusts its vacuum expectation value to. Sorry?
It's not massive.
It is?
It's not massive.
No, it's not. Here, it has to be massless apart from what is going to come out of this. I know you have written massless, sorry, you have made this point before, but yeah, so it has to be massless apart from what comes out of this term. So this is the axion thingy, or nearly max. So because of this term, so the axion solves the strong CP problem, we are very happy, and we can actually test the solution of the strong CP problem by discovering the axion, which has a very clear predictions coming from the structure that I described before. So, and the predictions come from the fact that the axion, because of the term I wrote before, it mixes with the pseudoscalar mesons, with the etas and with the pi zeros, from which we can compute that it gets a mass, which is related with the parameters of the chiral Lagrangian, with the pion masses, and is suppressed by the axion decay constant. This is the value. And also, we get couplings to quarks or nucleons of the pseudoscalar structure that Mark was telling before, coupling to two photons originated from the mixing with pions and so on. And in some extended models, if you want to, you can start already with the axion having couplings to electrons. And this is very interesting from the phenomenological point of view. Now, the point is that the mass, the couplings, they appear as in good Goldstone boson models, suppressed by this high energy scale, and this makes them perfect wisps in a sense, because the smaller the mass is, the weaker the axion would interact with standard model particles. So this can of course be generalized to any pseudo Goldstone boson that appears in the high energy completion of the standard model, or string axions that have been very nicely discussed so far. And so one of my tasks here is just to acquaint you with this plot, in which I just for the sake of concreteness, I decided to present the phenomenological implications of one of these particles, only focusing on the coupling to photons, okay, which I will write G as G, And in this parameter space, we see the mass of the possible action-like particle and the coupling to the photons and the scale of the coupling to the photons. And I hope that you will know a little bit of what's going on here by the end of this talk. Also, if I will briefly mention other possible wisps that Mark didn't have time to discuss very much. So let me just highlight. I will be talking about the so-called hidden photons, which are nothing but so the gauge bosons of a hidden U1 symmetry, or a symmetry which does not interact. A sector that does not interact at tree level with the standard model, but however, due to higher mass messenger particles that can couple to both, it can actually end up having some contact with the standard model. And if this is the case, well, this would be the natural connection with the standard model. This diagram that generates the so-called kinetic mixing. This is a very field theoretical way of seeing it. I'm sorry about that. So the size of the kinetic mixing is typically, as I was telling you, that of a radiative correction, but this is only like a tree-level statement, because actually if one develops models in which the gauge couplings in the hidden sector are much weaker, precisely in these large volume scenarios, this could be the case. So the kinetic mixing being proportional to the gauge coupling will be also much smaller, and also much smaller than the size of a radiative and typical radiative correction. Also, the kinetic mixing can be smaller if there are cancellations between different contributions to the kinetic mixing, and that will be the case if the hidden U1 is not originally a hidden U1, but is embedded in a non-abelian theory, for instance. So again, as in the case of the action-like particle I was showing you before, this parameter space of kinetic mixing and mass for the hidden photons is huge and has plenty of phenomenological consequences to explore. So let's start from the beginning to explore these consequences. So the beginning is the beginning, and but what's now? What is left now from the beginning? So we have a fantastic way of parameterizing essentially the history of the universe, sometimes called the standard cosmological model, or the standard model of cosmology, which unfortunately has, or very fortunately has, three ingredients, or let's say two ingredients: dark energy and dark matter, from which we don't know anything, and much might be that there's a third ingredient that I will be discussing in a short while: dark radiation as well. So three unidentified substances make a whole, make a lot of the energy content of the universe now. The question that we can ask is, can they be made out of wisps? And the answer is yes, or indeed. So let me just first discuss dark matter. And okay, so I just wanted to explain to you. Probably you all know this. So how? Sorry, there's some slides that went away. Yes. Very sorry. So this was actually the slide coming after the. Let's talk about dark matter thing. So can wisps account for the dark matter of the universe? Well, what do we know about dark matter? Actually, we all know two things, right? That is dark and is matter. So dark, not much more, unfortunately. Dark in the sense that it interacts very weakly, and this is extremely wispy, so that's perfect for our candidates. And matter is in the sense that the particles that form dark matter are non-relativistic, at least most of them. And this is not so wispy, might look like. However, the fact that these wisps have very weak interactions makes them actually perfect candidates for cold dark matter, because what would make our light particles non-relativistic are interactions with the primordial plasma, with the standard model, sorry. And since our wisps are wispy, they don't interact very strongly, so they cannot, or they can not very easily thermalize. So non-thermal mechanisms of producing dark matter actually will dominate, or can easily dominate. So indeed, the case of the action, in the case of the action, there are three non-thermal ways of building action dark matter, which turn out to give cold dark matter. These are the realignment mechanism, the decay of cosmic strings, and domain walls. So maybe I can just, I have to be very fast with this. So let me just, since the action, I can think the action is a Goldstone boson, let me just display this two-dimensional field space and draw the potentials. So this would be the potential of my complex scalar, whose phase is the action, and I'm just drawing the potential in 2 dimensions, not to completely destroy the symmetry. Oh, this is going to be hard. So I have the history of the action potential in a point is that at high temperatures, how can I stop this? No. It worked better before, but I cannot move the. Okay, well, let's see it. So at high temperatures, the symmetry, so we are in the phase respecting symmetry, but at low temperatures, the, fuck, okay, just see it. See the video and now I explain it. So I was supposed to stop the video in between. Well, what you saw is that at high temperatures, the Pacheco symmetry is respected. There's only one minimum. It's in the center of the field space. As the temperature goes down, the symmetry gets spontaneously broken, and the action field has to decide in which position it lays, and the potential is completely flat. So in this case, it was here. Okay. Then we made a zoom, and we waited a lot of time until the temperature had gone below around the QCD scale, because at when the temperature is around the QCD confinement scale, the potential that is going to solve the strong CP problem lifts up. It was suppressed at high temperatures. And then it makes the action finally roll and oscillate around its, the minimum, which is CP conserving here. Okay, so this happens in each point, in each point of the universe, with a random initial condition. Okay, and one can average over different domains in which the action would have different initial conditions, and one can find that the matter density in the form of so that the non-relativistic. Sorry. Of course, these oscillations, I forgot to say that, these oscillations are just precisely a very cold form of dark matter, just a condensate of non-relativistic actions. And the amount of dark matter in their form is given by this expression. So more or less you get the right amount if the action mass has 40 microelectron volts. So what are cosmic strings? So I told you that in each position of space, this the action field takes a different value. So it will, we will find in our universe, we will find occasions in which the distribution of the phase is such that there is a point at the center that cannot be in the minimum, for which the potential cannot be in the minimum. So it has to be, right? So this point here cannot make the action field continuous without going to the zero of phi, which has a lot of energy density. So if this is a two-dimensional cut of the universe, of course you have to imagine that in 3 dimensions this point is actually a string, one-dimensional object, which has a lot of energy density. And these cosmic strings, actually when they are formed at the Pacheco intercision, and they oscillate and they reconnect, and when they do so, essentially they emit actions. So they emit some action radiation, which typically is very non-relativistic. It's a very, you have to believe me in that. So, but at the QCD phase transition, so the potential lifts up, and if we are in this situation, the field starts to oscillate here and go to the minimum. Okay, so and most of the universe goes very close to the CP conserving minimum, except the part that topologically cannot escape, cannot get around action equal pi. And what happens here is that you will have a two-dimensional surface in one line here in this two-dimensional plane. In 3 dimensions it will be a two-dimensional surface in which the field is here at the QCD maximum. Now around these temperatures, so of course what we have is just precisely a cosmic string in the boundary of a domain wall, and these domain walls, if you are lucky, they shrink and decay into into axions again. And unfortunately, there's a controversy here between two groups and two types of understanding the dynamics of cosmic string evolution and domain wall decay that give very different contributions to the axion to the resulting axion dark matter density. So we have the group of Sekivi and Harari that say that the amount of dark matter is similar to the realignment mechanism, but Shella, Davis, and very recently the group of Kawasaki, Hiramatsu et al. In Tokyo University, I think, they also find they find a contribution which is typically 100 times larger, and would render axions to be perfect dark matter candidates for a much larger mass, which means a larger also decay constant, a smaller decay constant. Sorry. Of course, this is so. This was the case, one of the typical case. But if there's a period of inflation after the Pacheco transition, as it turns out, our universe fits in one of these domains, and therefore we cannot predict the dark matter density. Because we only have one realization of these random initial conditions, and this is the right amount of dark matter. And of course, if you tune the initial value of the misalignment angle, you can cope with very small masses or very large decay constants. You know very well. But unfortunately, the action is present during inflation, and this has some consequences, which is the imprint of isocurvature fluctuations in the CMB, which are very much excluded, and they will be very much more excluded, or a factor of 3 more excluded in Planck, or well, maybe discovered. So this is the summary of the axion phenomenology, or the axion dark matter phenomenology, in the one parameter which is free in the simplest axion models, which is the axion decay constant related with the mass. So here you say that, here you see that axion due to the axion dark matter due to the misalignment mechanism could populate this range if there's some entropy production after the Kinsey phase transition, and in the case in which the contribution of a string and strings and domain walls is significant, axion dark matter can be up to here. So, and these are astrophysical bounds that I will have not a lot of time to talk about. If we well, something very interesting is that what I told you about the axion is in general true for any Goldstone boson or any axion-like particle, even if its mass does not come from instantons and does not lift at very late times. So what we have here is in this parameter space is we have to be able to see axion, or a generalization of axion dark matter for a Goldstone boson that has this coupling to photons. But first of all, let me just tell you that this part of the parameter space corresponds to bounds from laboratory astrophysics, that in this part the axion-like particle decays into 2 photons and cannot be dark matter, and here the photons coming from the decay of the axion would be observable as a kind of universe radiation, which is not there. So what the remaining parameter space is what we selected in our paper as a possible parameter space where axion-like particles can be actually dark matter. Okay, so there is the value for which the misalignment mechanism would give the exact value of the dark matter density would be this line, and models in which are below would be given naturally much more dark matter, but they can be the right model if one considers entropy dilution and so on. Up here we have axion-like particle models in which the mass of the axion-like particle turns up very late in the history of cosmology, and therefore the dilution of dark matter is a little bit decreased. And here we have models that we don't know, but they could still be dark matter because there are no other possible constraints on their existence. So in this band here, there are the typical axion models, and you see that where the axion band, so the theory axion band crosses this bunch of models, is where precisely these experiments, haloscope searches, are looking for. 5 minutes. Okay, another example. So I wanted just to tell you that this happens for Goldstone bosons, like action-like particles or stringy actions can happen, but it also can happen for other types of bosons. For instance, for hidden photons, it was proposed by Nelson and Schultz 1 hour ago, also 1 year ago or so. However, and what we did in our paper is just essentially ratify that this can be a solution. So this can be the case. So vector boson can also give you this type of Bose-Einstein condensate dark matter, so sort of. But there are some constraints from cosmology because this condensate is able to interact with the standard model bath, so with the primordial plasma. And here, for instance, it can produce CMB distortions in the CMB in the power, not in the power spectrum, but in the black body spectrum. Here would give a contribution to the number of effective neutrinos, and so on. Well, here there would be some decay constraints. And well, there are some things more to say about this kind of action dark matter, but this kind of wispy dark matter, which do not make this model so exciting, and is the fact that typically, so the field is diluted during inflation, unless one allows this hidden photon to have couplings to, well, non-standard gravitational couplings. That, well, but I can explain you a little bit later because I'm running out of time. So let me just talk very briefly about the possible existence of dark radiation also in the universe. So the dark radiation is this little thing here that would be completely unnoticed today, but if we go back in the history of the universe, of course, the importance of radiation grows. And if we go to matter radiation equality, the amount of dark radiation could be quite sizable. So normally what we do is just we put the amount of energy in neutrinos and dark radiation in the quantity that we call NF, the number of the effective number of neutrino species, which is just the energy density on dark radiation stuff, divided by a normalization constant, which is given in terms of the photon density, essentially, and is what would be a standard, the contribution of a standard neutrino in a standard cosmological model. So there are some hints to the existence of this radiation from CMB studies, essentially from the study of large-scale structure that can be seen in the CMB, and also in studies of in counts of galaxies and clusters. And I shall not enter into details. Perhaps the most interesting figure to remember is this combination of the South Pole Telescope data plus WMAP7 plus other large-scale structure data, which points to the existence of one additional neutrino with an error bar which is not so big. There are others with bigger errors. And the very nice point is that we will, so if this is so, Planck has a lot to say. And actually, if I'm not mistaken, we can expect the results of Planck regarding the extra radiation by January next year. So this question will be settled if this 3.9 is a 3.9 or a 3.0. There are also some hints of the existence of dark radiation from Big Bang nucleosynthesis, where the universe, where the dark radiation was even more noticeable because there was no matter. And so I just show you the results. So both from the abundance of helium and deuterium independently. So we see, if we take the estimations of the primordial abundance of deuterium from Pettini et al. 2008, and the helium abundance from Isotov and Joan of 2 years ago, we see that actually they intersect the predictions from Standard BBN values slightly larger than 3. Okay, that would be the 0 here. So this is this band. Unfortunately, the problem is that there are no bright prospects to improve the accuracy in this measurement. So maybe we have to live with that. So I just wanted to tell you how can we get this dark radiation from these wisps that I was telling you before. Well, in principle, a coupling, actually like particle coupled to the photon, will be produced thermally to some extent in the early universe. The problem is that, well, even if this production mechanism is mechanism is very effective. So the contribution will only be 1 bosonic degree of freedom, which corresponds to NF equal to 4/7. So it's not a very big thing. And the required couplings to do so are in this region that I told you is excluded. So there are no very bright prospects for finding. So if we find dark radiation, cannot be a simple action-like particle model. However, it can be a hidden photon, and the reason is because hidden photons are produced pseudothermally in the early universe by resonant conversions from photons into hidden photons. So what happens is that an amount of photons converts into hidden photons, and this not only puts some hidden photons into the game, but also removes some photons. And remember that the amount of neutrino radiation that we put in NF, it's measured with respect to the amount of photons. So if we have removed photons and we have put them into hidden photons, the amount of NF can be very large. Okay. So actually, well, this corresponds to more or less the value I given you before, but with a slightly larger error bar. In this band you would have the extra radiation that is hinted by CMB and BBN, and there's this little corner in parameter space that corresponds to milli-electron volt masses and 10 to the minus 6 values of kinetic mixing that is not excluded by anything and is being looking for by laboratory experiments and could give extra radiation during CMB times. So this is an interesting region. Just to tell you that also Planck will tell us if hidden photons are there or not, because the sensitivity will reach even lower values. So I've made it to the end of cosmology. Promise that astrophysics is going to be very fast. So you probably all know that 1 minute is not enough to talk about astrophysics. That we can get very strong constraints from astrophysics by comparing numerical simulations in which we incorporate the emission of wisps or axions from stars with observations, okay? Because the emission of axions or other wisps accelerates the nuclear so the consumption of nuclear fuel and typically accelerates the stellar evolutions. So it's very interesting to point the work of several people in the recent years that have pointed out that actually the white dwarfs could be actually showing up this kind of anomalous extra cooling, and they attribute this cooling to the production of axions in Bremsstrahlung of electrons and nuclei, and they have not studied what could happen in the case of other wisps. So it's an open question if this has to be really an axion with a coupling to electrons or can be other thing. But actually one can see this cooling in two different observables. One is the white dwarf luminosity function that shows us the number of white dwarfs per volume and luminosity, which is essentially a tracer of a standard. Of white dwarf cooling. Okay, because white dwarfs they're death stars that cool down very slowly. So the faster they cool, the less time they spend in a given luminosity, but also in a variable star in which the cooling rate is related with the period decrease of the luminosity oscillations. So these two observables point to an axion, as Mark was saying, with a coupling to electrons in the range of 10 to the minus 14, and since this coupling to electrons is essentially given by a coefficient of order 1, depending on the model, the electron mass times the axion decay constant for couplings of order 1, one gets axion decay constants of order 10 to the 9. So another very interesting hint that could be around pointing the existence of an axion-like particle is the anomalous transparency of the universe to gamma rays, but I really don't have time to talk about this. But my summary of so let me just go to my summary of astrophysics, is that much exciting as these hints they can be, they will never provide us with a firm discovery. And they can only hint at targets in parameter space or model space to study further in laboratories or in your desk. However, there's one exception, and this is the fact that if some particles are produced in stars, they will be produced by our sun, And we can set up a laboratory experiment here on Earth and try to detect them. So we can just use the star as the particle producer of our laboratory. And this has been done with very successfully, although they didn't find anything, by a number of groups. In particular, so it's a relative success. In particular, the group of the CERN Axion Solar Telescope has has looked for the emission of axions that would convert into photons inside a magnetic field and would show up as X-rays in a detector. And they have been able to put the strongest constraints here. So basically they can exclude axions or axion-like particles with a coupling 10 to the minus 10 inverse GeV. And the most exciting thing for me is that actually there can be a follow-up, a humongous experiment that has been is being proposed by the same people of CAST, would be much wider because CAST uses an LHC dipole that has essentially a hole like this to detect axions. And well, these gentlemen, they are proposing a kind of LHC toroid, an atlas magnetic field to have a much bigger acceptance, much longer, and only dedicated to axion searches. And with this beast, if it's ever realized, the sensitivity can go down a little bit more than 1 order of magnitude.
Would that be based on CERN as well?
This is under discussion. So CERN is one of the natural candidates, but I think the discussion is open to everything. But there are no strong postulants to host the experiment so far. So the same game can be done for hidden photons, because hidden photons oscillate from photons, and they can be produced in the sun and detected. But in this case, we don't need magnetic field. And some experiments have been the same axion helioscopes can be recycled to put limits on hidden photons, but also an experiment is being taken place in Hamburg, which is what we call T-SHIPS, a telescope for solar hidden photon search, that will be releasing data very soon. And so I made it to the experiments in -1 minute. Rather than describing them and getting you nervous because you need your coffee, let me just go to the end, which is I think very interesting. So there's a number of experiments in the world looking for axion dark matter and wispy dark matter, and looking for subtle effects in the propagation of photons that could be due to the existence of wisps that couple to photons. So there are a number of sites immersed in this quest. And very recently, we made a report for the Department of Energy in the US, where we summarized essentially the possible experimental opportunities that we have now and we can do in the future in this report that is available also as an archive preprint, and where a bit of theory, phenomenology, and experiments is all put up. And just to perhaps scare you a bit, so these are the summary plots of the report, where bounds from astrophysics in blue, or NOR observations in green, and laboratory experiments in very dark green are shown, together with the possible prospects for a brilliant wispy future are shown in phosphorescent blue, green. So the same for the axion, the same for hidden photons, and these finally are my conclusions.
Yeah, just to understand something, in the analysis of ALPs which are not axions, you assume as a coupling only couplings to photons, or also to other?
In the analysis of?
ALPs, I mean the axion-like particles,
yes,
which are not axions.
Yeah.
In which the mass, and there's no relation between the mass and the decay constant.
Yeah. Here, for not lying and being concise, I assume that in all the phenomenology that determines these bounds, the coupling to photons is the one that dominates. And this might be or might not be the case, but There are some very important bounds that come from astrophysics, that the white dwarf cooling and the supernova bounds, which do not appear here. Well, the supernova is here, but it's really ridiculous. But if the action-like particle has a natural couplings to supernova, to nucleons or to electrons, there will be more bounds. But so we have to complement this plot of this parameter space with similar one constraining the different couplings. But it's very difficult to put this into dimensions.
These couplings could be reduced through the couplings like you have to photons to have to gluons.
Yeah, yeah, okay, what happens with the coupling to gluons?
Like QCD.
So far, so if you have one action-like particle with a couple to gluons, is the axion, and would have very similar. So it would live in this parameter space, just essentially one parameter, apart from some order one, or maybe not order one. So it would be the axion. If you have two, I think nobody has dig down in the possible phenomenology. But
no, the standard axion has a relation between the mass and the decay constant.
Yeah.
Here you don't assume such a relation.
exactly.
So you could, what I'm asking is what happens if you include also, is for such action-like particles in which there is no relation between the mass and the decay constant,
You put a coupling.
a coupling to gluons in the same way that you put couplings to photons.
Well, you
perhaps a different decay constant.
So this action-like particle would get a contribution to its mass from QCD.
Okay.
So that would forbid this part of the plot. I think,
Oh, I see.
because you would have a minimum mass.
Because only one gets massive. Only one gets massive, and the other are.
Is there, you didn't mention, so there's been this proposal about looking for axions by, by measuring the energy levels of cold molecular systems. Is there any progress in actually trying to do that?
I'm a bit decoupled of these experimental efforts. Actually, I don't know if so. The idea has been put up already for some time, but I don't know if there's a group that is actually doing it. I know that the same theorists that proposed it, they were still dealing with some details that in a sense they have to convince the experimentalists that these theoretical estimates are not completely out of the question. So they have to find exactly the atomic system that could, for instance, give enough sensitivity, and then unfortunately it will take I think a long time to have first results, because already the more or less optimistic estimates are a bit below the expectation, so the expected signals. So it will take a lot of refinement in the experiment to reach the observable level for a QCD axion. One could find an action-like particle that actually is also called dark matter, but has a stronger coupling to photons. This could happen. But at the moment I don't think there's a laboratory in which this thing is being set up.
Since we're running a little bit behind, maybe we'll just thank the speaker and have the short.